Time itself was born from chaos. In the first fleeting moments after the Big Bang, the universe was a blur of pure energy, a place where the very concept of a second held no meaning. This is the story of when time first slowed down, the universe's great shift from a formless frenzy to a cosmos of stunning order. By the end, you will understand the delicate chain of events that allowed everything from atoms to galaxies to form. We will uncover how a seething primordial soup settled into the structured reality we know, and why a single, critical transition made our existence possible. What does it mean for our reality that time itself had a beginning? This initial chaos was a universe of pure potential, a seething ocean of energy where the rules of physics as we know them did not yet apply. Within the first incomprehensibly small fraction of a second, during what is called the Planck epoch, the cosmos was a realm of quantum foam. Here, space and time themselves were not smooth and continuous but bubbled and frothed, constantly fluctuating. Particles and forces were merged into a single, unified entity. There was no light, no matter, no distance you could measure, because the concepts of here and there were not stable. It was a state of maximum disorder, a blur of constant creation and annihilation where time had no consistent arrow, and the very idea of a past and future was meaningless. Then, in an event of monumental importance, gravity peeled away from the other fundamental forces. This was the first great separation, the first step toward creating a universe with distinct laws. Following this, the infant cosmos underwent a growth spurt of staggering proportions known as inflation. In a span of time far shorter than a blink of an eye, the universe expanded faster than the speed of light, smoothing out the initial violent wrinkles and irregularities. This inflationary period was the universe's first deep breath, stretching the quantum foam into a far larger, smoother, and colder arena. It was this expansion that imprinted the faint seeds of structure we see etched into the cosmic microwave background, the afterglow of the Big Bang. These tiny ripples in temperature, variations of mere millionths of a degree, were the blueprints for everything to come. They were the subtle imperfections in an otherwise smooth canvas, the gravitational anchors that would one day pull matter together into the vast cosmic web of galaxies. How could such a frenzied beginning ever settle into the stable, predictable cosmos we observe now? The answer lies in the universe's most critical transformation, a great cooling that changed everything. This sudden, exponential expansion was the universe's great smoothing. In less than a trillionth of a second, space itself stretched from a size far smaller than a single proton to a volume that could encompass our entire observable cosmos and beyond. Picture a single microscopic wrinkle on the surface of a balloon. As the balloon inflates to an immense size, that tiny wrinkle is stretched so thin it becomes a vast, gentle curve. That is precisely what inflation did to the infant universe. It took the violent, chaotic quantum fluctuations of the Planck epoch and stretched them into colossal, macroscopic ripples. These ripples were subtle variations in density, tiny pockets where the universe was ever so slightly more crowded than elsewhere. They became the architectural blueprints for the entire cosmic web, the future sites of galaxies and galaxy clusters. This theory, championed by physicist Alan Guth, solved profound puzzles. It explained the horizon problem, the mystery of why the universe looks so uniform in all directions. Distant regions of space that should never have been in contact somehow share the exact same temperature. The only way this makes sense is if those regions were once intimately connected, pressed together before inflation blew them apart. The rapid expansion also flattened the overall geometry of the cosmos. just as inflating a balloon makes its surface appear flatter and flatter. This great smoothing did not erase all variation, however. It took the universe's initial chaos and traded it for a new, more subtle kind of order. The driving engine behind this phenomenal growth was a hypothetical field permeating all of space, known as the Inflaton field. Its energy propelled the exponential expansion, and as that energy decayed, it released a torrent of particles and radiation, reheating the cosmos in a fiery burst. This event filled the universe with a hot, dense plasma, setting the stage for the next great act. This end of inflation is a critical mystery. What caused this field to lose its energy and bring the breakneck expansion to a halt? The answer seems to be a process called graceful exit, a phase transition where the Inflaton field settled into a lower energy state, its work complete. The violent stretching stopped, and the universe transitioned into the slower, more measured expansion we see today. This moment marks the true beginning of time's deceleration, the shift from a frantic, formless beginning to a cosmos where the first recognizable patterns could finally emerge. With the frantic stretching of inflation over, the universe began to breathe at a more measured pace. Time itself was finally slowing down. Think of it as a wild, raging river coming into a wide, meandering flow. This deceleration was not just about the expansion of space, but a fundamental change in the rhythm of existence, governed by the principles of general relativity. As the cosmos cooled and its energy density dropped, the very curvature of spacetime evolved, stretching out the seconds and allowing events to unfold in a clear, sequential order for the first time. This new, slower tempo was absolutely critical. It meant that the universe's building blocks could finally assemble themselves without being instantly torn apart. When the temperature plunged below 10 million billion Kelvin, a profound transition occurred. The strong nuclear force, one of the fundamental forces of nature, gained the upper hand. For the first time, it could permanently bind the frenetic quarks swirling in the primordial soup into stable particles, creating the protons and neutrons that are the bedrock of all atomic matter. This was the moment the universe gained lasting solidity. In this newly ordered era, radiation still dominated, but matter was beginning to make its presence felt. The slower passage of time allowed for a process of breathtaking importance, Big Bang Nucleosynthesis. For about 17 minutes, the entire cosmos functioned as a single, immense nuclear furnace. Protons and neutrons collided and fused in a controlled, systematic dance, forging the first atomic nuclei. This was not a chaotic explosion, but a precise and predictable chain of nuclear reactions. It produced the universe's first light elements, primarily hydrogen and helium, in proportions that match almost perfectly what we observe in the oldest stars today. This 17-minute window of creation is a direct result of time's deceleration. If the universe had remained in its earlier, frenzied state, these reactions could never have proceeded in such an orderly fashion. The elements of life were forged not in an instant but through a deliberate, timed process. This new temporal order set the stage for the next great cosmic milestone, one that would literally bring the universe out of the darkness. How did this gradual cooling influence the way matter began to clump together, paving the way for the formation of atoms and the liberation of light itself? That foggy, glowing plasma had persisted for nearly 400,000 years, a superheated soup where light was perpetually trapped. Then, the universe cooled to a pivotal threshold of around 3,000 Kelvin. At this temperature, the frantic dance of particles finally slowed enough for a fundamental union to occur. Electrons, which had been bouncing wildly off photons, were suddenly captured by atomic nuclei, forming the first stable neutral atoms. This event, known as recombination, transformed the cosmos in an instant. The universe, which had been an impenetrable, glowing fog, suddenly became transparent. For the first time, photons could travel freely across vast distances without constantly colliding with matter. This ancient light, released in that great moment of clarity, still washes over us today as the cosmic microwave background radiation. It is the oldest picture we have of the universe, a baby photo etched onto the sky. The patterns in this afterglow are not random. They are the frozen echoes of sound waves that rippled through the early plasma, acoustic oscillations created by the push and pull of gravity and radiation pressure. When matter and radiation decoupled, these waves were imprinted onto the light, leaving a precise record of the universe's density at that exact moment. Satellites like Planck have mapped these subtle temperature variations with incredible precision, revealing the subtle lumps and bumps that were the gravitational seeds for all future structure. With the intense radiation pressure now gone, matter was finally free to collapse under its own weight. But ordinary atoms were not the only players in this gathering darkness. A mysterious, invisible substance known as dark matter had been quietly waiting in the wings. Unlike normal matter, dark matter does not interact with light at all. It had already begun to clump together within the cosmic blueprint laid out by inflation, forming vast, invisible scaffolds. Now, with the universe transparent and calm, these dark matter halos provided the gravitational anchors onto which the first clouds of hydrogen and helium could gather. This was the true beginning of cosmic architecture, the moment when the subtle imperfections from the dawn of time started to grow into the grand design of galaxies. How did these first, fragile structures defy the expanding universe and coalesce into the brilliant islands of stars we see today? These invisible scaffolds of dark matter began to pull the cosmos into shape. Think of them as a vast, unseen skeleton, a framework woven through the expanding emptiness. While the brilliant fog of the early universe had cleared, allowing light to travel freely, it was this dark architecture that truly dictated where things would go. Dark matter, mysterious and invisible, does not emit, absorb, or reflect light. Its only language is gravity, and as the universe continued its measured expansion and cooling, these dark matter particles, once moving at speeds close to light, began to slow down significantly. This deceleration was the key that unlocked cosmic structure. Because the particles were now moving slowly or were cold, they could effectively clump together. They began to pool in the deepest gravitational wells of those ancient inflationary ripples, collapsing into vast, sprawling halos. This process is best described by the cold dark matter model. It tells a story of hierarchical growth where the smallest structures form first. Tiny dark matter clumps emerged, acting as cosmic seeds. Over billions of years, these seeds merged and collided, building up into larger and larger halos through a process of hierarchical merging. Supercomputer simulations, like the famous Millennium Run, illustrate this evolution with stunning clarity. They show a universe transforming from a nearly smooth distribution of matter into an intricate cosmic web, a network of dark matter filaments connecting at dense nodes where giant galaxy clusters would eventually reside. This was not a random scattering, but a coordinated growth, a shift from chaos to an immense gravitational order. These dark matter halos provided the essential stability for ordinary matter, the atoms of hydrogen and helium, to finally collapse. Without the gravitational anchor of a dark matter halo, the slight pressure from leftover radiation and the inherent motion of gas would have prevented atoms from gathering into anything significant. The dark matter acted as a deep gravitational well, a cosmic trap. vast clouds of pristine gas were drawn into these invisible halos, swirling into flattened disks. Within these nurturing cradles, the gas could cool, fragment, and finally ignite. How did ordinary matter follow this dark blueprint to create the first stars and galaxies? This brings us to the cosmic dawn, the moment the universe finally lit up with its first brilliant points of light. Deep within the nurturing cradles of dark matter, the first stars were born. These were not like the stars we see today. They were titans, behemoths of pure hydrogen and helium that ignited in the profound blackness of the cosmic dark ages. Astronomers call them population 3 stars, forming in the dense cores of those primordial gas clouds. They were likely hundreds of times more massive than our Sun, and they burned with a ferocious, short-lived intensity. Their birth was the universe's true dawn, the moment it finally switched on the lights. The ultraviolet radiation pouring from these first stars was so powerful, it began to fundamentally alter the fabric of space itself. This radiation ripped electrons away from the neutral hydrogen atoms that filled the cosmos, retransforming the diffuse gas into a hot, ionized plasma in a process known as cosmic reionization. Imagine a cold, dark landscape suddenly pierced by a few brilliant, isolated lighthouses. Around each lighthouse, the intense beam burns away the fog, creating a growing bubble of clarity. That is precisely what happened. Each of the first stars created a vast, expanding bubble of ionized hydrogen, a zone of transparency within the opaque neutral medium. The lives of these stellar giants were spectacularly brief. They exhausted their nuclear fuel in only a few million years, a mere heartbeat in cosmic time, and then died in cataclysmic supernova explosions. These violent deaths were as important as their births. For the first time, the universe was being seeded with heavy elements, the carbon, oxygen, and iron that are the essential ingredients for planets and for life. This was the first act of cosmic recycling, enriching the pristine gas with the materials for everything that would follow. The sheer mass of these first stars dictated the pace of this enrichment. Their immense gravity pulled in gas so efficiently that they likely formed with a very top-heavy initial mass function, meaning there were many more high-mass stars compared to later generations. This ensured that the early universe was quickly flooded with both intense radiation and the first heavy elements. This period of reionization was not an instant event. It was a gradual, patchy process that unfolded over hundreds of millions of years. We have observational evidence for this drawn from the most distant quasars, brilliant beacons powered by supermassive black holes. The light from these quasars travels across the universe to reach us, and on its journey, it passes through clouds of neutral hydrogen. By studying the absorption lines in the quasar spectra, astronomers can see how the hydrogen fog gradually thinned. Early in the universe, the light shows strong absorption from vast tracts of neutral gas. Later, the absorption becomes patchier, and eventually the fog is mostly gone, indicating the completion of reionization. This great transformation had a profound feedback effect on the cosmos. The intense heat from the radiation created pressure that could blow gas away from developing galaxies, temporarily stifling further star formation in small halos. This feedback mechanism helped regulate the growth of the earliest structures, ensuring that only the most massive dark matter halos with gravity strong enough to hold onto their gas could continue to form stars. How did this newly ionized and enriched universe pave the way for the more stable, long-lived galaxies we recognize today? Those first brilliant bubbles of starlight were the seeds of something far grander. Within the protective grasp of their dark matter halos, these early protogalaxies began a long process of assembly. The subtle density fluctuations imprinted by inflation, once microscopic ripples, were now vast gravitational wells pulling in surrounding gas and smaller structures. This was hierarchical clustering in action, a cosmic building project where small structures merge to form larger ones. Picture a quiet, flowing river gathering countless streams and tributaries, gradually swelling into a mighty, continent-spanning waterway. That is how galaxies grew, not in isolation, but through a relentless process of attraction and merger over billions of years. The pristine hydrogen and helium gas, drawn into these halos, did not simply collapse into a star-forming frenzy. It often settled into vast, rotating disks, a direct result of the halo's inherent angular momentum. This spin is what gives us the majestic spiral galaxies we see today, like our own Milky Way, with their elegant arms winding around a bright central core. Not all galaxies took this graceful form, however. Violent collisions between proto-galaxies, occurring over billions of years, could scramble this orderly rotation. These cosmic mergers stirred up the gas and stars, randomizing their orbits and giving birth to the rounder, featureless shapes of elliptical galaxies. The incredible diversity of galaxy morphologies we observe, from elegant spirals to bloated ellipticals, is largely a fossil record of their unique merger histories. This growth was not unchecked. A critical regulator emerged in the form of feedback, particularly from active galactic nuclei. At the heart of many young galaxies, a supermassive black hole would feast on the infalling gas, becoming an immensely powerful engine. The colossal energy released by this accretion did not just create a brilliant quasar, it also blew fierce winds back into the galaxy. This feedback acted as a cosmic thermostat, heating surrounding gas or ejecting it entirely, thereby shutting off the fuel supply for new stars and limiting the galaxy's growth. This intricate dance between gravity pulling material in and feedback pushing it out created a surprising correlation, a signature of the new cosmic order. We observe a tight relationship between the mass of a galaxy's central bulge and the mass of its supermassive black hole, and an even more fundamental connection between the properties of the visible galaxy and the mass of its encompassing dark matter halo. The Hubble Ultra-Deep Field provides a stunning visual testament to this entire process. This iconic image, a long exposure staring into a seemingly empty patch of sky, reveals thousands of galaxies at various stages of assembly. We see tiny, irregular blobs, the infant protogalaxies from the early universe, alongside majestic, fully formed spirals and galaxies caught in the act of violent mergers. It is a single frame capturing billions of years of cosmic history, a direct window into the hierarchical growth of structure. This grand architecture, from stars to galaxies to clusters, all unfolded within a universe whose expansion was gradually slowing under the pull of gravity. Yet, this very expansion was about to enter a new and mysterious chapter, one that would once again reshape the destiny of the cosmos. This accelerating expansion introduces a profound new rule to the cosmic order. For billions of years, gravity had been the dominant architect, tirelessly pulling matter together to build galaxies and clusters. Now, a mysterious repulsive force, which we call dark energy, has taken command of the universe's large-scale dynamics. Its discovery at the end of the 20th century was a complete shock to astronomers. By meticulously observing distant supernovae, teams of researchers found that these stellar explosions were fainter than expected, meaning they were farther away than they should be in a universe slowing down under gravity. The inescapable conclusion was that the expansion of the cosmos is not just continuing, it is speeding up. This is like tossing a ball into the air and watching it not only fail to fall back down, but instead shoot away from you faster and faster. The primary candidate for this mysterious driver is the cosmological constant, a concept Einstein once proposed and later discarded. It represents a constant energy density inherent to the fabric of empty space itself, a vacuum pressure that stretches spacetime and pushes galaxies apart. The key to its behavior is described by its equation of state, a parameter that dictates how its pressure relates to its energy density. For the cosmological constant, this value implies a relentless, negative pressure that remains constant over time, ensuring the acceleration continues indefinitely. The evidence for this is now overwhelming. Data from the Planck satellite, combined with extensive supernova surveys, paints a consistent picture of a universe whose expansion is accelerating, governed by a simple and predictable set of rules. This new order has a chilling consequence for the future of cosmic structure. As dark energy comes to dominate the universe's energy budget, its repulsive effect actively suppresses the growth of new galaxies and clusters. The gravitational pull that once drew matter together is now being overwhelmed on the largest scales. The cosmic web, that magnificent network of filaments and nodes, will begin to fray. Over trillions of years, galaxies not already bound in local groups will be pushed apart by the stretching space between them, leading to an increasingly isolated and homogeneous cosmos. Each island universe will be left alone in a vast, dark, and ever-expanding sea. This acceleration also warps our perception of time itself. In the far future, the relentless stretching will cause extreme time dilation effects for any hypothetical observer. The light from the final, dying stars in other galaxies will be so stretched and redshifted that it will become undetectable, effectively freezing their final moments from our view for all eternity. How does this grand acceleration influence the universe's thermal history and its inherent disorder? The connection is direct and profound. As space expands, it cools, and the cosmic microwave background radiation, the remnant heat from the Big Bang, will continue to drop toward absolute zero. Yet the total entropy or disorder of the universe continues to increase. Every star that burns out, every black hole that slowly evaporates, adds to this cosmic chaos. The accelerating expansion does not stop this process, it ultimately facilitates it. By isolating galaxy clusters and eventually individual galaxies, it creates a cosmic landscape where energy differences can no longer be harnessed, and all processes slowly grind to a halt in a state of maximum entropy. This relentless rise in disorder is inextricably linked to the arrow of time, the one-way direction from an ordered past to a disordered future that defines our very experience of reality. This relentless rise in disorder defines the very arrow of time we experience. From our memories to the burning of a star, every process flows in one direction, from a more ordered past toward a more disordered future, governed by the second law of thermodynamics. This law states that the total entropy of an isolated system always increases. Our universe in its entirety is that ultimate isolated system. The profound mystery is not that entropy increases today, but why it was so incredibly low in the beginning. The Big Bang represents a state of astonishingly low entropy, a condition of exquisite order that set the clock ticking. Without this initial fine-tuning, the cosmos would have been born into a state of maximum chaos, a featureless soup where stars could never form and time would have no consistent direction. The formation of a galaxy or a planet is a local event that creates order, but it does so at a great cost. As gravity pulls a diffuse cloud of gas into a dense, brilliant star, the entropy of that cloud locally decreases. It becomes more structured, yet this process releases a tremendous amount of energy, primarily as light and heat, which radiates out into the cold emptiness of space. The increase in entropy from that radiated energy is vastly greater than the local decrease from forming the star itself. The universe pays for its pockets of order by creating even more disorder in its surroundings. Black holes are the ultimate expression of this cosmic bargain. They are entropy powerhouses. A black hole's entropy is not found in its mysterious interior, but is instead proportional to the surface area of its event horizon, the point of no return. This means that a single supermassive black hole contains more entropy than all the stars, gas, and particles in the entire galaxy it anchors. When matter falls into a black hole, it effectively erases a vast amount of complex, low-entropy information and replaces it with an immense, simple, high-entropy state on the horizon. This process drives the universe's total disorder upward in a single, dramatic leap. The ultimate fate of these cosmic engines is tied to a quantum quirk predicted by Stephen Hawking. Empty space is not truly empty. It is a seething froth of virtual particle pairs constantly popping in and out of existence. At the very edge of a black hole's event horizon, one of these particles can fall in while the other escapes, stealing a tiny amount of the black hole's mass. This is Hawking radiation. Over incomprehensible eons, this process causes even the largest black holes to slowly evaporate. But this evaporation creates a deep puzzle, the black hole information paradox. When a black hole finally vanishes, what happens to all the information about the matter that fell into it? According to quantum mechanics, information cannot be destroyed. Yet, if the black hole evaporates completely, leaving behind only random Hawking radiation, that information seems to be lost forever, violating a fundamental law of physics. This paradox suggests that our understanding of gravity, quantum mechanics, and thermodynamics is incomplete. Some theories, like the holographic principle, propose a radical solution that the information is not lost but is encoded on the surface of the event horizon like a cosmic fingerprint. The resolution of this paradox may lie in a theory of quantum gravity, which would also explain the universe's initial low-entropy state. Perhaps the conditions of the Big Bang were not a random accident, but a necessary outcome from a deeper physical law, a universe naturally emerging from a quantum fluctuation with an inherent temporal order. Meanwhile, dark energy weaves its own thread into this tapestry of disorder. As it accelerates the expansion of space, it dilutes the density of matter and radiation, pushing galaxies apart and creating a colder, more vast, and ultimately more disordered cosmos. The universe is marching irreversibly toward a state of thermodynamic equilibrium, a cosmic heat death where no energy can be harnessed, no stars shine, and no processes occur. Time, as we understand it, may even lose its meaning. In this grand narrative, our very existence is a fleeting, beautiful eddy in a relentless current flowing from order to chaos, a temporary structure made possible by the universe's most profound and initial gift, a moment of impossible order at the dawn of time. A black hole acts like the universe's ultimate vacuum cleaner, swallowing stars, gas, and light, seemingly erasing every trace of what falls in. This creates one of the most profound conflicts in modern physics. Quantum mechanics, the rulebook for the very small, insists that information can never be truly destroyed. If you could somehow reverse time, you should in principle be able to trace the history of every single particle. Yet a black hole appears to violate this sacred principle, consuming information and leaving behind only a few simple properties like mass, spin, and charge. This is the black hole information paradox, a direct challenge to our understanding of cosmic order. The formation of these cosmic vacuums begins with the collapse of a massive star. When such a star exhausts its nuclear fuel, its own immense gravity causes it to implode catastrophically, crushing its core into a point of infinite density called a singularity. This singularity is shrouded by the event horizon, a boundary in spacetime from which nothing, not even light, can escape. For an outside observer, time appears to freeze at this horizon. A clock falling toward a black hole would seem to tick slower and slower, never quite crossing that final threshold from our perspective. It is a place where the normal flow of time, as we know it, breaks down completely. Stephen Hawking made this puzzle even deeper with his revolutionary theory of Hawking radiation. He realized that the intense gravity at the event horizon could coax pairs of virtual particles into real existence. In this quantum process, one particle falls into the black hole while the other escapes, carrying away a tiny bit of the black hole's energy. Over staggering timescales, this causes the black hole to slowly evaporate, shrinking until it potentially vanishes entirely. Hawking initially believed that the radiation escaping was completely random and thermal, carrying no information about what fell in. If that were true, then when the black hole disappears, the information is lost forever, violating quantum law. This conflict pits the deterministic, smooth spacetime of general relativity against the probabilistic, information-preserving world of quantum mechanics. One compelling solution is the holographic principle. This radical idea suggests that all the information about everything that falls into a three-dimensional black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint etched onto its surface. Think of it as the most advanced storage device imaginable, where the entire volume of the black hole is described by information on its boundary. This leads to another dizzying puzzle, the firewall paradox. If information is being encoded and radiated back out from the horizon, does that mean the horizon is not the smooth, empty space general relativity predicts, but a searing wall of high-energy particles that would incinerate anything crossing it? We are now testing these wild ideas with real observations. When two black holes spiral together and merge, they release torrents of gravitational waves, ripples in the fabric of spacetime. By carefully analyzing the signals from these collisions detected by observatories like LIGO and Virgo, physicists are searching for subtle echoes or other signatures in the data that might reveal what happens at the event horizon. How does resolving this paradox shape our view of the universe's fundamental laws? It suggests that spacetime itself may be an emergent property, a hologram arising from a deeper, more fundamental quantum reality. This forces us to look back to the very beginning, to a time when the entire cosmos was perhaps as simple and enigmatic as a black hole's core. The quantum realm is never truly still. Even in what we call empty space, a seething dance of virtual particles constantly flickers into existence and vanishes again. These are quantum fluctuations, temporary borrowings of energy from the vacuum itself. In the universe's first frantic moments, the colossal energy of the Inflaton field amplified these tiny, random ripples, stretching them from the subatomic scale to sizes larger than the observable universe. What began as fleeting, microscopic wrinkles in the fabric of spacetime became the grand blueprints for the entire cosmic web. This is the profound link between the chaotic quantum world and the ordered cosmos we see today. The random variations in energy density created by these fluctuations were the only imperfections in an otherwise perfectly smooth early universe. They were the subtle lumps in the cosmic dough, the places where matter was ever so slightly more dense. Without them, gravity would have had nothing to grasp, and the universe would have remained a featureless, expanding haze forever. The specific pattern of these initial seeds holds the key to their origin. The theory predicts a nearly scale invariant spectrum, known as the Harrison-Zeldovich spectrum. This means that the fluctuations had roughly the same amplitude or strength, regardless of their size. Whether you look at a region that would become a single galaxy or a massive supercluster, the initial density variation was about the same. This particular pattern is a direct fingerprint of the inflationary period, a telltale sign that the universe underwent that phenomenal stretching. As the universe cooled and time's pace slowed, these quantum jitters froze into place, transforming from probabilistic quantum events into definite, classical density perturbations. They became permanent features etched into the cosmos. We can still read this ancient imprint today in the cosmic microwave background. Satellites like WMAP and Planck have mapped the faint temperature differences in this afterglow with exquisite precision. The hot and cold spots they see are the direct descendants of those primordial quantum fluctuations. The statistics of these spots are Gaussian, meaning their distribution follows a classic bell curve, just as you would expect from random quantum noise. This is a powerful confirmation that the largest structures in the universe were seeded by the smallest possible events. The gravitational pull of these slightly denser regions began to act like a cosmic amplifier. Over hundreds of millions of years, dark matter, responding only to gravity, pooled into the deepest of these gravitational wells. Ordinary matter, the hydrogen and helium gas, was then pulled in after it. The tiny initial overdensities, perhaps only 1 part in 100,000, were steadily magnified. A region that started with just a tiny bit more mass than its surroundings would pull in more and more material from the neighboring areas, growing richer and denser over time. This process, known as gravitational instability, is what sculpted the vast web-like structure of the modern universe, with its great filaments of galaxies connecting at dense nodes and surrounding immense, empty voids. This entire cosmic architecture, from the smallest dwarf galaxy to the largest supercluster, finds its origin in the random, frenetic energy of the quantum vacuum, stretched and frozen into permanence during the universe's first moment of ordered change. This intricate cosmic web is the largest structure we know, a sprawling network of galaxies threading through the emptiness. It looks like a delicate spiderweb spun on an unimaginable scale, with brilliant clusters of galaxies gathered at the intersections of long, dark filaments. These threads are composed of dark matter, the invisible skeleton upon which the luminous universe is draped. This entire architecture emerged through a slow, gravitational ballet, a direct consequence of those initial density fluctuations from the dawn of time. The measured flow of time was absolutely essential for this construction project. It allowed for a process called hierarchical structure formation, where small clumps of dark matter merged over billions of years to build ever larger halos. Picture a quiet river delta where countless small streams gradually converge into a few mighty rivers that finally empty into the sea. That is how the cosmic web was built, through a relentless process of attraction and merger. The precise pattern of this web was not random. It carries a specific echo from the universe's early plasma, known as Baryon acoustic oscillations. Before the cosmos became transparent, the universe was a hot soup where ordinary matter, or baryons, and radiation were locked in a tight embrace. Gravity would try to pull matter into denser regions, but the intense radiation pressure would push it back out, creating spherical sound waves that rippled through the plasma. When the universe cooled enough for atoms to form, this pushing stopped instantly, freezing these waves in place. The result was a preferred scale, a standard ruler imprinted on the distribution of matter. We see this today as a subtle statistical tendency for galaxies to be separated by a specific distance, about 500 million light-years. This predictable scale allows astronomers to measure cosmic distances with tremendous accuracy, tracing how the web has stretched over the eons. The growth of this vast network was also influenced by the most elusive of particles, neutrinos. These ghostly particles, streaming through the universe in vast numbers, have tiny but measurable masses. Because they travel at near light speed, they tend to smooth out the very smallest wrinkles in the cosmic web, slightly suppressing the formation of the tiniest galaxies. Their impact is a faint but crucial signature woven into the web's grand design. Our most detailed map of this architecture comes from monumental efforts like the Sloan Digital Sky Survey. This project has painstakingly measured the positions and redshifts of millions of galaxies, creating a three-dimensional chart of the local universe. When you look at these maps, the web pattern is undeniable, a stunning confirmation of the cold dark matter model. It reveals a universe of breathtaking order, with great walls of galaxies, vast empty voids, and dense, brilliant clusters. These galaxy clusters are the final nodes of the cosmic web, the largest gravitationally bound structures in existence. They can contain thousands of galaxies, all swarming within a common halo of dark matter. But the galaxies themselves are only a small part of the story. The space between them is filled with a superheated gas known as the intracluster medium. This plasma is so hot that it glows in X-rays, and it contains far more ordinary matter than all the stars in all the cluster's galaxies combined. The very existence and properties of this hot gas tell a profound story about the cluster's history and the nature of the cosmic order that formed it. How does this searing intergalactic medium reveal the violent past of these cosmic metropolises? And what does it tell us about the mysterious dark matter that holds them together? These colossal assemblies are the final nodes of the cosmic web, immense cities of galaxies where thousands of island universes swarm together. Yet the stars you see in these galaxies are only a tiny fraction of the story. The true bulk of a cluster is found in the space between them, a superheated gas known as the intracluster medium. This plasma is so incredibly hot, reaching temperatures of millions of degrees, that it glows not in visible light but in powerful X-rays. How does a gas become so hot? The answer lies in the violent process of the cluster's own birth. As matter fell into the cluster's immense gravitational well over billions of years, it crashed in at speeds of thousands of kilometers per second. These colossal collisions create powerful shock waves, much like sonic booms on a cosmic scale, that heat the gas to these staggering temperatures. The energy released by supermassive black holes at the hearts of member galaxies, active galactic nuclei, also pumps tremendous heat into this environment, stirring the cosmic cauldron. This searing plasma is a rich repository of heavy elements, iron and oxygen forged in generations of stars, and then blown out into the void by supernova explosions and galactic winds. We can detect this tenuous, glowing gas through a remarkable phenomenon called the Sunyaev-Zeldovich effect. As the ancient light from the cosmic microwave background passes through a galaxy cluster, the hot electrons in the intracluster medium give the photons a tiny energy boost. This creates a distinct, shadowy imprint on the microwave background, a cold spot that allows astronomers to map the cluster's gas even without seeing its X-ray emission directly. This effect is a powerful tool for discovering the most distant clusters in the universe. The sheer existence of these massive, relaxed clusters tells us a profound story about cosmic history. After the turbulent era of mergers, a kind of order emerges. Through processes known as violent relaxation and phase mixing, the galaxies and the dark matter within the cluster settle into a state of gravitational equilibrium. It is a shift from chaotic construction to a stable, ordered system, a final product of the universe's long journey from initial chaos. Perhaps the most stunning evidence for the dominance of dark matter comes from a cosmic crash site known as the Bullet Cluster. This is actually two clusters that have collided and passed through one another. Observations show that the hot X-ray emitting gas, the ordinary matter, was slowed down and stuck in the middle of the collision by the friction of its own interactions. But the dark matter, which does not interact with anything except through gravity, sailed right through the crash. By mapping the cluster's mass using gravitational lensing, astronomers found that most of the mass is not where the gas is, but in two separate clumps ahead of the collision, exactly where the dark matter would have traveled. This is like seeing two ghosts walk through a car crash completely unscathed, leaving the wreckage of the cars behind. The bullet cluster provides direct, visual proof that dark matter is real, and that it is the primary ingredient holding these cosmic metropolises together. By counting clusters of different masses across cosmic time, we can trace the history of structure formation itself. The number of massive clusters we see at different eras acts as a sensitive probe of the universe's expansion history and its total matter content. Fewer clusters than expected would tell us one story about dark energy, while more would tell another. This cluster mass function is a crucial ruler for measuring the very parameters of our cosmos. Within these vast structures, a fierce regulatory battle is waged. The same intracluster medium that reveals so much about the cluster also acts to stifle star formation in its member galaxies. As a galaxy orbits through this hot gas, the pressure strips away its cool, star-forming hydrogen in a process called ram pressure stripping, leaving behind a galaxy that is red, dead, and devoid of the fuel for new stars. This is how the universe enforces order, by quenching the fire of creation within its largest gravitational prisons. How does this grand architecture, from the quantum scale to the cosmic web, ultimately define the arrow of time and the universe's inevitable fate? The universe's entire history is written in a few key numbers. These cosmological parameters are the fundamental settings for reality itself, governing the expansion rate, the cosmic composition, and the ultimate fate of everything. They are the numbers that allow us to run the cosmic film backward and forward with astonishing precision. We now know our universe is geometrically flat, meaning parallel lines never meet, and its total mass energy density is exquisitely balanced at the critical value. This flatness is not an accident. It is a direct prediction of the inflationary theory, that phenomenal stretching in the first instant which ironed out any primordial curvature. The dominant framework that brings all these measurements together is the Lambda CDM model. Lambda represents the cosmological constant, the dark energy driving accelerated expansion, while CDM stands for cold dark matter, the invisible scaffolding for cosmic structure. This model is the standard model of cosmology, a remarkably simple recipe that successfully describes almost everything we see, from the earliest light to the largest galaxy clusters. Our ability to measure these parameters with such confidence comes from a powerful trio of observational pillars. The cosmic microwave background gives us a precise snapshot of the infant universe, a baby picture from 380,000 years after the Big Bang. The subtle patterns in its temperature, mapped by satellites like Planck, are a frozen record of the density fluctuations that would later grow into galaxies. Supernovas serve as cosmic mileposts. By observing how the light from these exploding stars dims with distance, astronomers discovered the universe's accelerating expansion, revealing the presence of dark energy. And Baryon acoustic oscillations provide a standard ruler etched into the cosmic web. The tendency for galaxies to be separated by a specific scale allows us to measure how the universe has stretched over billions of years. When these three independent lines of evidence are combined, they tell a consistent and compelling story. The Planck mission, for instance, determined the universe's age to be 13.8 billion years. It revealed a cosmos made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. This means everything we see and are made of is just a tiny fraction of the cosmic inventory. Yet this triumphant story of precision is not without its puzzles. A significant tension has emerged around the Hubble constant, which measures the current expansion rate of the universe. Measurements based on the cosmic microwave background, which look back to the very early universe, suggest one value, but measurements using nearby stars and supernova, which measure the universe's current expansion, consistently yield a faster rate. This discrepancy is more than a minor calibration issue. It could be a hint of new physics, perhaps a property of dark energy that changes over time, or a new type of neutrino. Alternatively, it might point to a subtle, undiscovered systematic error in our measurements. This tension reminds us that science at the frontier is a living process where anomalies drive progress. Despite this, the overall consistency of the data is breathtaking. The fact that observations of the ancient universe and the modern universe align so well, save for this one key tension, provides overwhelming support for the standard model. The parameters are so tightly constrained that we can now ask profound questions about the initial conditions that set everything in motion. How do these precisely measured numbers inform our understanding of the universe's violent birth? The specific pattern of fluctuations seen in the cosmic microwave background is a direct test for theories of inflation. The data strongly favors a nearly scale invariant spectrum of primordial fluctuations, exactly what most inflationary models predict. The measured value of the spectral index, which describes how the strength of these fluctuations varies with scale, tells us about the specific shape of the Inflaton field's potential energy. It is as if we are reading the engineering specs of the universe's first moment from the ancient light that fills the sky. This incredible backward projection allows physicists to test models of the universe's genesis with real data, moving cosmology from pure speculation into a rigorous science of the beginning. The journey from a seething quantum foam to a cosmos defined by a handful of elegant numbers is the ultimate story of order emerging from chaos, a narrative whose final chapters we are only now beginning to write. The early universe was a natural particle accelerator of unimaginable power, a laboratory where energies dwarf anything we can create on Earth. Within this primordial forge, the inflationary period left behind more than just density ripples. It should have shaken the very fabric of spacetime, generating waves known as primordial gravitational waves. These are not waves of sound or light, but literal ripples in the geometry of the cosmos, stretching and squeezing space itself as they travel. Their detection would be our most direct window into the universe's first fraction of a second. The primary way we hunt for these ancient tremors is through the cosmic microwave background, specifically its polarization. Light from the early universe can be polarized in specific patterns, much like sunlight reflecting off a lake. Scientists classify these patterns into two types, E modes and B modes. The E modes are curl-free patterns, primarily generated by the density fluctuations we already understand. The B modes, however, contain a telltale curl, a swirling signature that can be created by the gravitational waves from inflation. Finding this specific B mode pattern in the CMB polarization is the holy grail of observational cosmology. It would be the smoking gun for inflation itself. The strength of this signal is quantified by a key number called the tensor-to-scalar ratio. This ratio measures the relative amplitude of these gravitational wave ripples compared to the density ripples. A detection would not just confirm inflation, it would tell us the incredible energy scale at which it occurred, potentially linking it to the realm of grand unified theories where forces merge into one. The search for this signal is one of the most challenging endeavors in modern science. A famous example is the BICEP and Keck array collaboration at the South Pole. They announced a tantalizing possible detection in 2014, only to later find, with the help of the Planck satellite data, that the signal they were seeing was largely contaminated by interstellar dust within our own galaxy. This painstaking work to distinguish the faint cosmological signal from local foregrounds continues to push the limits of our technology. New projects are now taking up the mantle. The upcoming Light BIRD satellite, along with advanced ground-based telescopes like the Simons Observatory, are being designed with unprecedented sensitivity. They aim to scan the sky with such precision that they can filter out the dust and hopefully isolate the true primordial signal. The stakes could not be higher. Detecting these waves would do more than confirm a rapid expansion. It would give us a glimpse of physics at the scale of quantum gravity, a realm where spacetime itself may have a quantum granular structure. This pursuit also opens the door to profound and speculative possibilities. Some models of inflation suggest it could be eternal, with our entire observable cosmos being just one bubble in a vast, ever-expanding multiverse where different regions have different physical laws. The quest to measure the universe's first shivers is fundamentally a search for our own cosmic origins, connecting the largest scales of the cosmos to the very smallest rules of reality. At the very edge of our understanding lies a moment where all our familiar rules dissolve. To comprehend the Planck epoch, we must venture into a realm where time and space themselves lose their classical meaning, becoming a seething, probabilistic foam. This is the domain of quantum gravity, a theoretical frontier where the smooth canvas of general relativity merges with the chaotic uncertainty of the quantum world. In this state, spacetime is not smooth and continuous. It might be composed of discrete, vibrating loops, as in loop quantum gravity, or exist in 10 dimensions, as string theory suggests, with all but 3 of them curled up into an impossibly small size. Here, before 10 to the power of -43 seconds, the 4 fundamental forces of nature were fused into a single, unified superforce. The universe was a quantum fluctuation on the grandest possible scale, a place where the very ideas of before and after, of cause and effect, become ambiguous. How could such a state of ultimate chaos give rise to the ordered cosmos we see today? Some theories propose our universe did not begin with a singularity, but with a bounce. In this scenario, a previous cosmos contracted to an incredibly dense state before rebounding in our Big Bang, forever avoiding the mathematical nonsense of infinite density. This concept of a cyclic universe elegantly sidesteps the problem of a true beginning, suggesting the cosmos has no start and no end, only an eternal rhythm of contraction and expansion. The holographic principle offers another radical perspective, proposing that all the information describing our 3-dimensional universe could be encoded on a 2-dimensional boundary surrounding it, much like a complex pattern on a cosmic bubble. This idea intimately links gravity to quantum information, treating spacetime as an emergent property from a more fundamental, information-based reality. But can we ever test these mind-bending ideas? The search is on for faint imprints left by these primordial processes, certain anomalies in the cosmic microwave background, or subtle patterns in the large-scale structure of galaxies, might one day reveal the fingerprints of a pre-Big Bang phase or the granular nature of spacetime itself. These observations could provide our first experimental window into quantum gravity. This brings us to the most profound question of all. How did the arrow of time, the relentless flow from a low entropy past to a high entropy future, emerge from such a timeless, chaotic beginning? Perhaps the universe was born with an inherent quantum preference for order, a single, random fluctuation that selected our reality from a vast landscape of possibilities, setting the cosmic clock ticking for the very first time. These precise physical laws feel almost too perfect for our existence. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If it were weaker, galaxies and stars could never have coalesced from the expanding chaos. This apparent fine-tuning of the cosmos raises a profound philosophical question. Are we simply the beneficiaries of an incredibly lucky cosmic lottery, or does the universe's capacity for order hint at something deeper? This is the heart of the Anthropic Principle, a reasoning that turns the question on its head. We observe a universe capable of fostering life because we are here to observe it. In a cosmos with different physical constants, no one would be around to wonder why things are the way they are. This perspective does not necessarily provide an answer, but it reframes the entire inquiry. It suggests that our very presence acts as a filter, selecting from a vast array of possible universes the one set of rules that allows for complexity and consciousness. This line of thinking naturally leads to the Multiverse Hypothesis. What if our orderly universe is just one bubble in an infinite, frothing sea of cosmic domains, each with its own unique laws of physics? In this vast landscape, most universes would be stillborn or chaotic, incapable of supporting any structure. We, of course, find ourselves in one of the rare, hospitable outliers. This idea finds a curious echo in a classic thermodynamic puzzle known as the Boltzmann brane paradox. The physicist Ludwig Boltzmann speculated that in an eternal and mostly random universe, a fully formed, self-aware brain could spontaneously fluctuate into existence from the chaos, complete with false memories of a past. If such disembodied observers were more likely than the gradual evolution of an entire ordered cosmos, then statistically, you and I should be those random, isolated minds, not products of a 13.8 billion-year cosmic evolution. The fact that we are not, that we observe a consistent and vast history, strongly suggests our universe began in a state of exceptionally low entropy, setting a firm and reliable arrow of time. This deep connection between cosmic order and the flow of time brings us back to our own fragile place in this grand scheme. The local pockets of order we represent, from a single cell to a thinking brain, are temporary eddies in a relentless cosmic current flowing toward greater disorder. Our ability to contemplate the universe is a direct consequence of this grand transition from chaos, a fleeting moment where the laws of physics align to create islands of structure capable of looking back and understanding their own origins. This realization inevitably shapes our search for meaning and for other life. If the universe is so vast and its laws so conducive to order in the right conditions, then the emergence of life elsewhere seems not just possible, but perhaps inevitable. Our cosmic journey, from the first slowing of time to the formation of stars and planets, may be a story repeating itself across countless worlds, each a testament to the universe's profound and mysterious capacity for creating order and perhaps consciousness. Our planet is a testament to the universe's capacity for creating islands of order. Life itself represents a local rebellion against the cosmic tide of entropy, a complex, self-sustaining system that maintains its intricate structure against the pull of disorder. This remarkable phenomenon depends entirely on the universe's long, patient journey toward structure. From the gravitational collapse of galaxies to the gentle spirals of protoplanetary disks, every step was a necessary prelude to creating stable environments where life could take root. The concept of a habitable zone is central to this search. This is the orbital region around a star where the temperature is just right for liquid water to exist on a planet's surface, not so close that it boils away nor so far that it permanently freezes. It is a delicate balance, a cosmic sweet spot where the chaos of stellar formation gives way to the potential for biological order. Our own sun's habitable zone allowed Earth to become a cradle, a world where complex chemistry could evolve into biology over billions of years. This timescale is not an accident. It required a universe where time itself had slowed to a steady, predictable rhythm, allowing for the gradual, incremental process of evolution to unfold. The very ingredients for life were forged in the chaotic hearts of long-dead stars. Elements like carbon, oxygen, and nitrogen were synthesized through nuclear fusion and then scattered across the galaxy by supernova explosions. These stellar cataclysms, while violent, were essential acts of cosmic recycling. They enriched vast clouds of gas and dust with the heavy elements necessary to form rocky planets and the complex molecules that life is built upon. When our solar system coalesced from such an enriched cloud, it carried the legacy of those ancient stars, providing Earth with a rich inventory of the essential elements for life. To frame the search for other civilizations, scientists use the Drake equation. This is not a single answer, but a framework for thinking about the many factors involved. It multiplies terms like the rate of star formation, the fraction of stars with planets, the number of planets in habitable zones, the fraction where life actually emerges, and the fraction where that life develops intelligence and technology. While many of these factors remain unknown, each new discovery, like the thousands of exoplanets identified by the Kepler mission, fills in a piece of the puzzle. We now know that planets are common and that many stars host worlds orbiting within their habitable zones, but a planet's location is just the beginning. Long-term habitability depends on a host of stabilizing factors. Plate tectonics, for instance, act as a global thermostat for a planet like Earth, recycling carbon and regulating the climate over geological timescales. A protective magnetic field shields the surface from harmful stellar radiation, and a stable atmosphere provides both a buffer and the chemical ingredients for life. The next great step is to search for biosignatures, which are chemical signs of life, in the atmospheres of these distant worlds. Using powerful telescopes like the James Webb Space Telescope, astronomers can analyze the starlight that filters through an exoplanet's atmosphere. An abundance of oxygen alongside methane, for example, would be a tantalizing clue, as these gases react quickly and would not coexist for long without a biological source constantly replenishing them. The possibility of life elsewhere is the ultimate expression of the universe's drive toward self-organization. It suggests that given the right conditions and enough time, the same physical laws that govern galaxies and stars can give rise to complex, ordered systems that can look back and contemplate their own origins. This profound connection between cosmic history and biological potential leads us to a final, inevitable question about the ultimate destiny of this grand, self-organizing experiment. The universe's grand narrative is one of structure slowly unraveling. Dark energy's relentless push will stretch the cosmic web to its breaking point, isolating every galaxy cluster in an ever-expanding sea of nothingness. Within these isolated islands, the era of star formation will inevitably cease. The last stars will flicker out roughly 100 trillion years from now, their fuel exhausted, leaving behind a cosmos populated only by the cooling embers of white dwarfs and neutron stars. The universe will enter a degenerate era, a profoundly dark age where no new suns ignite to pierce the eternal night. This is not a sudden end, but a gradual fading, the final victory of entropy over the delicate order that allowed for galaxies and life. The very protons that form the bedrock of all atomic matter may not last forever. Speculative physics suggests that over incomprehensible timescales, perhaps after 10 to the power of 34 years, protons themselves could decay, causing every remaining atomic structure to gently dissolve into a faint haze of subatomic particles. Even the mightiest structures, supermassive black holes, are not eternal. Through the slow trickle of Hawking radiation, they will evaporate over staggering eons, taking on the order of 10 to the power of 100 years to vanish in a final, silent flash. As the cosmos expands at an accelerating rate, our observable universe will paradoxically shrink. The light from all but the most gravitationally bound neighboring galaxies will be stretched beyond detectability, their wavelength shifted into oblivion. The cosmic microwave background, the fading afterglow of creation, will cool and dim until it is indistinguishable from the absolute cold of empty space. We are left with a vision of the universe's final state, a cold, dark, and nearly featureless equilibrium known as heat death. In this distant future, with no energy gradients left to harness and no processes occurring, the very concept of time may lose all meaning. There is no before or after, only a permanent, unchanging state. This ultimate fate is a direct consequence of the universe's initial low entropy, the very same exquisite order that set the arrow of time flying in the first place. Could this be the only possible outcome? Some cosmological models suggest more violent alternatives, like the Big Rip, where dark energy grows so strong it tears apart galaxies, stars, and even atoms themselves in a final catastrophic moment. Others imagine a cyclic universe where a new Big Bang emerges from the ashes of the old, perhaps through a quantum bounce. These speculative scenarios challenge the finality of heat death, suggesting our orderly cosmos might be just one chapter in an infinite story. This profound connection between the beginning and the end forces us to look back at the moment of inflation. The same process that seeded our universe with structure may be eternally creating a multiverse, a vast collection of cosmic domains, each with its own laws and fate. Our universe, with its specific constants that allow for a long, rich history of order, may be just one rare bubble in an infinite froth of possibilities. How does our fleeting existence, nestled between the initial chaos and the final silence, shape our search for meaning in a cosmos destined for such a cold and distant end? Our universe may be just one fortunate bubble in an endless, frothing cosmic sea. This is the staggering implication of eternal inflation, a theory suggesting the rapid expansion that shaped our cosmos never truly stopped. Instead, it continues forever in the broader background, while local regions, through random quantum fluctuations, suddenly settle down, each becoming a separate universe with its own unique properties. In this eternal foam, new bubble universes are constantly being born, each with potentially different physical laws, different fundamental constants, and even a different number of spatial dimensions. The vacuum energy that drives inflation can take on many different values, and this value dictates the very rhythm of time within each bubble. A universe with high vacuum energy might expand so frantically that particles never have a chance to coalesce into atoms, while one with low energy might collapse back on itself instantly. Our orderly cosmos, with its just right expansion rate and stable nuclear forces, is not a miraculous accident, but simply one of the rare, habitable outcomes in a vast, mostly inhospitable ensemble. This multiverse framework offers a powerful answer to the fine-tuning problem. Instead of asking why our universe's constants are so perfectly set for life, we recognize that in an infinite array of possibilities, a tiny fraction of universes will, by sheer statistics, have the right conditions. We inevitably find ourselves in one of those. This landscape of possibilities finds a theoretical home in string theory, which suggests an astronomical number of possible stable states for the vacuum, perhaps 10 to the power of 500. Each of these vacua corresponds to a different set of physical laws, a different possible universe. This incredible diversity leads to a profound puzzle known as the measure problem. How do we assign probabilities in an infinite multiverse? If an infinite number of universes contain life and an infinite number do not, how can we say which outcome is more likely? Scientists are still grappling with how to define a cutoff or a measure that gives meaningful answers. While the multiverse might seem permanently beyond our view, it could leave subtle observational clues. If our bubble universe ever collided with a neighboring one in the distant past, the immense energy released could have left a peculiar, circular imprint on the cosmic microwave background, a kind of cosmic bruise. Astronomers have searched for these signatures, and while a few tentative anomalies have been proposed, none have been confirmed. The idea of a multiverse fundamentally reshapes the quest for a final theory. It suggests there may not be a single, unique set of equations describing one universe, but rather a meta-law, a framework that governs the possibilities across the entire multiverse. This shifts the goal from explaining why our constants have the values they do, to explaining why the landscape of possibilities is structured in a certain way. How could such a meta-law unify all the forces of nature into one coherent description of reality? The dream of a single equation that describes all of reality is the ultimate goal of physics. This theory of everything would unify the four fundamental forces, revealing them as different facets of a single, elegant framework. Think of it like water, which can appear as solid ice, liquid water, or gaseous steam, yet is always H2O. In the same way, gravity, electromagnetism, and the nuclear forces might simply be different phases or manifestations of one underlying universal field. This quest for unification drives our most ambitious theories, from supersymmetry to string theory. These are not just abstract games, they are attempts to answer why our universe operates by the specific rules it does, and why the constants of nature, like the mass of an electron or the strength of gravity, have the exact values that make our cosmos possible. The early universe provides the ultimate testing ground for these ideas. In its first moments of unimaginable heat and density, the forces we see as separate today were merged into one. As the cosmos expanded and cooled, they crystallized out in a specific sequence, like phases of matter freezing into place. The first unification occurred when the electromagnetic and weak nuclear forces merged into a single electroweak force. At even higher energies, theories suggest a grand unification where the strong nuclear force joins them. The final and most elusive step is merging this with gravity, creating a single rulebook for everything from the smallest quark to the largest galaxy. This hierarchical unification is challenged by puzzles like the hierarchy problem, which asks why the Higgs boson is so comparatively light when the scales of gravity are so immense. Supersymmetry, a leading candidate for new physics, offers a compelling solution. It proposes that every known particle has a superpartner or sparticle. These sparticles would help cancel out the extreme quantum effects that would otherwise make the Higgs impossibly heavy, naturally explaining its mass. The search for these sparticles is a primary mission for the Large Hadron Collider. While no definitive sign has been found yet, the hunt continues, pushing our machines to ever higher energies to probe the conditions where unification might occur. Another profound clue comes from a theoretical discovery called the AD-SC-FT correspondence. This is a kind of mathematical dictionary that translates problems in a gravitational universe with a certain geometry into problems in a quantum field theory without gravity on its boundary. It suggests a deep and unexpected link between the force of gravity and the behavior of quantum particles, hinting that spacetime itself might be an emergent property from a more fundamental, information-based reality. How could a final theory of everything illuminate the very first moment of the Big Bang? It might show that the initial conditions were not arbitrary, but the only possible outcome from a single, unified law. The same principles that govern the unification of forces could have dictated the onset of cosmic inflation, setting the arrow of time and the low entropy state that made our ordered universe inevitable. The initial singularity of the Big Bang is a boundary beyond which our physics fails. General relativity predicts a point of infinite density and temperature, a moment where time itself seems to begin. But infinities in physics are often a sign that our theories are incomplete, pointing toward a deeper truth where quantum mechanics and gravity must unite. The quest to understand this moment leads us to theories that erase the singularity entirely, suggesting a cosmos with no true beginning or end. In loop quantum cosmology, for instance, the universe did not emerge from a point of infinite density. Instead, a previous cosmic phase contracted to an incredibly dense state before quantum gravitational effects caused a rebound, a great bounce that launched our expanding universe. Time in this model is finite but unbounded, a continuous flow from a past epoch into our present, forever avoiding the mathematical paradox of a singularity. This cyclical view offers a compelling explanation for the universe's most profound feature, its arrow of time. The reason our cosmos began in a state of exceptionally low entropy could be traced directly to the conditions at the bounce. The pre-Big Bang phase might have been vast and ordered, and the bounce itself acted as a cosmic reset, transferring that order into our new expanding phase and setting the clock ticking forward. Other visions of the beginning are even more radical. The Hartle-Hawking no-boundary proposal imagines the universe as a smooth, self-contained geometry, like the surface of a sphere. In this model, there is no sharp, singular beginning, just as the North Pole is a point on a globe but not an edge. Time simply emerges from this timeless, finite geometry, a seamless transition from nothingness to a universe governed by physical law. Meanwhile, the ekpyrotic model paints a dramatic picture of our three-dimensional universe as a membrane or brain floating in a higher dimensional space. Our Big Bang could have been triggered by a collision with another such brain, a colossal but gentle impact that infused our reality with energy and set it expanding, all without a singular start. These ideas are not just philosophical speculation, they may one day be tested. The cosmic microwave background, that ancient afterglow, could potentially hold faint imprints of a pre-Big Bang phase. Certain patterns in its polarization or subtle non-Gaussianities, deviations from the standard random distribution of hot and cold spots, might carry the signature of a bounce or a brain collision. Finding such a signal would be like discovering a fossil from a previous cosmic era. How do these theories account for the stunning uniformity and flatness we observe? Inflation remains the most robust explanation, but even it can be framed within a cyclical or eternal context. The great smoothing could have occurred during the contracting phase before the bounce, or as a consequence of the brain collision itself, preparing the universe for the orderly expansion we see today. Inflation is the leading story for our universe's smooth beginning, but it is not the only tale told by the mathematics. A cosmos born from a great bounce offers a compelling alternative. In this cyclic model, our expanding universe did not erupt from a singularity but rebounded from the collapse of a previous cosmic phase. Time itself resets at each bounce, with the immense contraction naturally smoothing and flattening the cosmos, preparing it for a new cycle of expansion. This endless rhythm of death and rebirth provides an elegant solution to the horizon problem without any need for a brief, frantic period of super-fast stretching. Another radical idea comes from string gas cosmology, which proposes that the early universe was a hot, dense gas of the fundamental strings proposed by string theory. In this scenario, the mutual interactions and winding modes of these strings could have prevented the universe from collapsing to a point and naturally led to a smooth, stable state, setting the stage for the orderly expansion we observe. Some physicists have even explored the possibility that the speed of light was not always constant. A varying speed of light in the very early universe could have allowed distant regions to communicate and equalize their temperature, again solving the horizon problem without invoking inflation. Each of these frameworks tells a different story about the shift from chaos to order, challenging the inflationary paradigm and forcing us to ask deeper questions about our origins. The critical test lies in their unique predictions for the ancient light that fills our sky. While inflation predicts a nearly perfect scale invariant spectrum of primordial fluctuations, some bouncing models can produce a distinct red tilt, a subtle deviation in how the strength of these ripples changes with their size. The detailed patterns of polarization in the cosmic microwave background are another key battleground. The specific swirling B-mode pattern, the holy grail for inflation, might be absent or look very different in a cyclic universe. Furthermore, the statistics of the hot and cold spots hold vital clues. Inflation typically predicts that these fluctuations follow a Gaussian or bell curve distribution, meaning they are fundamentally random. Some alternative models, however, predict detectable non-Gaussianities, subtle correlations between the spots that would appear as strange, non-random alignments in the data. The Planck satellite has already placed tight constraints on these deviations, its data so far aligning beautifully with the simplest inflationary models. Yet the search for anomalies continues, with every tiny irregularity scrutinized for a hint of new physics. The next great leap will come from a new generation of observatories. Space-based gravitational wave detectors, like the proposed Laser Interferometer Space Antenna, LISA, could potentially detect a background hum of primordial gravitational waves, a fossil from the universe's birth. The specific frequency and amplitude of this signal would be a smoking gun, uniquely identifying whether the waves were generated by inflation, a cosmic bounce, or something else entirely. These future experiments will not just test theories, they will help us write the true first chapter of our cosmic story, revealing whether our universe is a one-time event or part of an eternal, repeating cycle. These next-generation observatories are not merely larger telescopes, but entirely new senses for humanity. They are designed to perceive the cosmos in ways we once thought impossible, from the faintest whispers of gravitational waves to the subtle radio hum of the universe's dark ages. The James Webb Space Telescope, for instance, acts as a powerful time machine, its infrared eyes peering through cosmic dust to witness the birth of the very first galaxies. It shows us the infant universe not as a theoretical concept, but as a realm of real, forming structures, testing our models of how chaos first coalesced into those initial islands of light. But this is only the beginning. On the horizon, instruments like the Laser Interferometer Space Antenna, or LISA, will open an entirely new window by detecting low-frequency gravitational waves. These are the ripples from truly colossal events, like the mergers of supermassive black holes at the hearts of galaxies, waves that have been washing through the cosmos for billions of years. They could even carry a faint primordial hum from the universe's first instant, a direct signal from the era of inflation itself. How do we listen to the silent epochs before the first stars? This is the goal of projects aiming to detect 21-centimeter radiation from neutral hydrogen. This faint radio signal is a fossil imprint from the cosmic dark ages and the subsequent dawn of reionization. By mapping this signal in 3 dimensions, observatories like the Square Kilometre Array will create a cosmic movie, showing us how the first stars and black holes literally lit up the universe, burning away the primordial fog. The synergy between these different methods is where the deepest secrets will be uncovered. multi-messenger astronomy, which combines gravitational wave detections with traditional telescope observations, has already revolutionized our understanding of neutron-star collisions. We now know these violent mergers are cosmic forges, creating vast clouds of heavy elements like gold and platinum. Each such event is a direct test of nuclear physics in the most extreme conditions imaginable. Another profound mystery these tools may solve is the nature of dark matter. Could it be made of primordial black holes, forged from dense lumps in the early universe? Observatories like the Einstein telescope, a future gravitational wave observatory, will be sensitive enough to detect the mergers of these hypothetical objects if they exist. Or perhaps dark matter will reveal itself through its subtle effects on the large-scale structure of galaxies, mapped in unprecedented detail by missions like the European Space Agency's Euclid. Every piece of data, from the polarization of the cosmic microwave background to the precise distances of millions of galaxies, tightens the constraints on our models. They help us answer whether our standard model of cosmology is complete, or if we are on the verge of discovering new physics that will once again reshape our understanding of time, gravity, and the universe's journey from a formless beginning to the structured cosmos we call home. This entire grand sequence, from the first quantum tremor to the last dying star, fits together with a breathtaking elegance. We can now trace a single, unbroken narrative of cosmic evolution, a story where the slowing of time itself allowed for the gradual construction of everything we see. The universe began in a state of hot, dense simplicity, a near-uniform soup of energy. As it expanded and cooled, time's pace became measurable and deliberate, permitting gravity to work its slow magic on the subtle seeds planted by inflation. Quantum fluctuations were stretched into cosmic blueprints, dark matter sculpted an invisible scaffolding, and ordinary matter condensed into the first stars and galaxies, all within a framework governed by a handful of physical constants. This is the power of the Lambda CDM model, our standard model of cosmology. It is a single, unified story that successfully predicts everything from the specific patterns in the cosmic microwave background to the vast, web-like distribution of galaxies observed in sky surveys. The model's success hinges on its ability to integrate data from wildly different eras. The ancient light from Recombination tells us about the initial conditions, while the distribution of nearby galaxies reveals how structure has grown over billions of years. The fact that these independent lines of evidence point to the same cosmic recipe, a universe made of 5% ordinary matter, 27% dark matter, and 68% dark energy, is a triumph of scientific reasoning. This consistency is not a lucky guess. It is rigorously tested using Bayesian statistics, a mathematical framework that allows cosmologists to compare different models against the mountain of observational data. We do not just prove one model right, we systematically demonstrate that all other plausible explanations are astronomically less likely. This process has solidified our big picture view, showing a cosmos that evolved in a specific hierarchical manner. The great mysteries that remain, like the true nature of dark matter, are not failures of the model but invitations for deeper exploration. Their resolution will likely require an even more profound synthesis, perhaps one that finally unites the physics of the very large with the rules of the quantum world. This unified cosmic history does more than just explain the past. It inspires a profound sense of connection. We are not merely observers of a static universe. We are active participants in an ongoing story of emergence, a narrative written into the fundamental laws of reality. How does this knowledge that we are woven into the fabric of a cosmos journeying from chaos to order shape our understanding of our own place within it. Our journey from a frenzied quantum blur to a cosmos of galaxies reveals a profound truth. The universe's greatest gift was not a sudden creation, but a gradual slowing, a deceleration of time itself that allowed structure to patiently assemble. This measured pace let gravity sculpt the invisible dark matter scaffolds, permitted the first atomic nuclei to fuse in a deliberate 17-minute window, and gave galaxies the billions of years they needed to merge and mature. We are the beneficiaries of this cosmic patience, living in a temporary pocket of order carved out from the relentless flow toward greater disorder. The very laws of physics that govern this process, from the strength of gravity to the mass of an electron, appear exquisitely tuned, as if the universe were always destined to become complex enough to look back and comprehend itself. This grand narrative of self-organization, from the tiniest quantum ripple to the vast cosmic web, underscores the breathtaking beauty and fragility of our existence. While the cosmos marches toward a cold and distant heat death, that final silence only makes the present chorus of stars, planets, and life more magnificent. Our story is not yet complete. The mysteries of dark matter, the true nature of the Big Bang, and the quest for a theory of everything remain the great frontiers of discovery. Each new telescope and particle detector brings us closer to understanding our place in this unfolding saga. So the next time you gaze at the night sky, remember you are not just looking at points of light. You are witnessing a living history, a universe that transformed chaos into order, and in doing so, made a home for wonder. We would love to hear what part of this cosmic story resonates most with you. Share your thoughts in the comments, and if you are eager to continue exploring, there are more videos waiting for you on our channel. Thank you for joining this exploration of when time first slowed down and our universe